In this project, we analyzed a DC servo motor system by analyzing its stability, modeling its dynamics, and by the method of the least square method, we could know the parameters of this system. We used a PI and PD controller to know the stability and performance via simulation. And finally, we could use a physical setup to see these analyses real time and configure all our variables to get the best results.
Having a second order system with unknown parameters, we use two different signals as inputs. The step signals give a stable response with no controller at all, so we use the controls just to see how it affected the signal. Also, the Gaussian noise was used to increase the variability of the inputs to the outputs, so we can apply the least square method to find these unknown parameters. As we can see, both values of the response are stable under the step signal because of the type system, but the first one has an undesired overshoot and too much oscillations. We can control this using a PD controller which relates a KD gain that affects on the natural frequency and the damping of the system for it to not have overshoot or oscillations. As we can see here, the system also follows a square signal, which was expected since it's able to follow a step signal. As we can see here, the system also follows a square signal, which was expected since it's able to follow a step signal. As we can see here, the system also follows a square. Even though the white noise was added for variability, we can see that the system is able to follow the reference of the white noise pretty well too. Even though the white noise was added for variability, we can see that the system is able to follow the.
After observing the schematic design about the DC motor, we could detect that it belongs to a third-order system. However, we had to make it a second-order system in order to apply the following methodologies. As it can be seen in our model, we have two parameters, where B corresponds to the gain, since it's the parameter in the numerator, and A corresponds to the damping, since it is the parameter which deals with electrical and mechanical damping.
To estimate the parameters of the model, we use the least square method. This method minimizes the error between a predicted model and the actual outputs taken by simulation or physical experimentation. To do this, we apply the inverse Laplace transform to our model, having in time domain and rewriting it as the equation shown below. A is a matrix with the values of the first derivative of the position applied with a high-pass filter by simulation, and the inputs of the system taken either by simulation or by the physical experimentation. Theta is a matrix that has the solutions for the values for A and B parameters, and B it's another matrix that has only the values for the second derivative, also given by the same filter by simulation. To find the parameters A and B of our plant, being B over S squared times AS, first we need to apply the inverse Laplace transform. Having this plant in the time domain, we can rewrite it as the form A equals theta B, for which solution applying the least squared method is theta equals this function below. In this function, you have a term that is A transpose times A, and it's inverted. For it to be a solution, this term should be invertible then. To assure that this term is invertible, we can check by using the eigenvalues of this term. If these eigenvalues are non-zero or bigger than 0, we can check that this solution exists, and therefore we can apply the least square method to our plant in the time domain to find parameters A and B.
For the analysis of our results regarding the position and velocity control of the DC servo motor. First of all, we have the PD controller for the DC servo motor for the position. As we can see, we have a slightly overshoot in the transient behavior, but in the end, we have the steady state behavior following the reference, fulfilling the Routh-Hurwitz criteria. We have the gains for this position controller equally the same, because we are assigned some complex conjugate poles that we are asked that our root locus must pass by. For the velocity control, we have a similar response, but we are using a PI controller for the DC servo motor. As we can see, we have a slightly overshoot greater than the last position controller in the transient behavior and some oscillations, but in the end it follows our reference, fulfilling the Routh-Hurwitz criteria. And finally, for the velocity control analysis, using also a PI controller, but with a difference that we are including a disturbance, we can see that the oscillations and the overshoot increases dramatically, but in the end, we can see that the system follows a reference. This tells us that no matter how greater the disturbances are, our PI controller can successfully handle these perturbations or disturbances in the steady-state behavior, as it fulfills the Routh-Hurwitz criteria successfully. To conclude our project, we can see that the derived dynamic model obtained and the transfer function accurately represents the DC servomotor's behavior, comparing the electrical damping and the damping, which is the mechanical one. We can estimate our parameters using the least square method, which ensures us precise modeling. The PI and PD controllers, respectively, effectively stabilize our system and optimize the position and velocity control for a desired input reference. Finally, our simulations confirm that the model's reliability and the controller's performance achieve the desired reference. Thank you very much.